I want to discuss filtering in the sense of the frequency response, which is really one of the cores of signal processing applications. I remind you that there's two components to the frequency response because it's a complex term. There's the magnitude response and the phase response. And I would say the more interesting term is the magnitude response, the gain, because it tells you the relative scaling it does to each frequency term to the original signal. And generally speaking, there's about 4 types of filters we use in applications, and I'll go through each of them. Let's flip a few slides, and let's start. The low pass filter. And as the name implies, what it says is that I want to have some data, and I want to retain all the low frequencies here and say, hey, these high frequencies are just too much for me. Let's remove them out. And what you would do is pre-design a frequency response-based signal that multiplies each of the low frequencies by a high number and all the high frequencies to a low number. So you can see anywhere between 0 to maybe like 180, we have a higher gain, and everywhere else you have your gain is actually decaying. What this would do to the signal, you can see here, if this is the blue noisy signal, then at the end of this, you'll have this orange signal, which is much more reduced than before. And that's what we would call, for example, denoising. Depending on application, you might want a high pass filter to retain all the high frequencies and reduce the low frequencies as the name applies. Again, you'll see how this is done in the frequency response-based analysis. So here's the magnitude response based on the frequency, and you'll see that at the high frequencies, you have a high gain, and at the low frequencies, you'll have a low gain. And what this does, you'll see the signal, you have this original data, and you see that you have a output filtered signal, which is all the high frequencies. It's a much different result, the opposite result of what you just saw in the low pass example. And other types of filtering that you will see is here's called a bandpass filter. And what the name implies is that there's a certain set of frequencies that you actually want to consider, and you want to remove everything else. Why would you do this? Well, you would do this in something like speech processing, for example. You would know, for example, that the human speech is only at a certain range of frequencies. Let's say it starts at 100 hertz and a bit more onward, 100 to 200 hertz. And maybe there's some background noise that you want to remove out, but you know that this is what you want it to be, but then that you're allowing. And so you allow the magnitude response to be high in this band and decay out outwards. And that's called a bandpass filter. And it would look something like this. This is how you get clean audio signals. And the last maybe filter that we might use is called the opposite of that, the band stop filter. And as the name might imply, is that there's a certain band of frequencies that you actually want to remove out, and you want to retain everything else. So here there's a low gain at these set of frequencies, and everywhere else is high. And in doing so, you will have some mix of frequencies, so maybe low and high, but there's no, it's not none. There's a reduced set of frequencies inside this band. As a sort of leeway into future topics of interest, one of the problems you might see is how we design these filters is that they're actually quite noisy. They're sinusoidal signals that are very noisy as well. And maybe that you don't want to design a frequency response that's oscillating. It should be quite smooth. And one of the historical developments related to this is what's called a Butterworth filter. And it's considered to be the classical example of a smooth filter that does exactly what you want it to do. So here there's no oscillations. It's just quite plainly designed to filter a frequency response, which is high at low frequencies and decays outward. There's no oscillations. If you want a high pass filter, you design a function that mimics that behavior. So at high frequencies, and you want on this end, it's going to be a larger gain. And you might design a bandpass filter. So these are the set of frequencies that are very nicely amplified or gained in this band. And the opposite end, you will see a band stop filter like this, very smooth signals. And I would say that I don't know if we do this in this course, but they're really worth investigating and looking up in terms of what you want to learn about how filtering works.